Welcome back, everyone. In this part of the lecture, we will focus on the second derivative test for relative extrema. Here, we will be determining if a function f has a relative extrema at a point with the aid of the second derivative at that point. Let us first introduce the theorem. Let f be a function such that f double prime exists for all values of x on some open interval containing x equals c, and f prime of c is equal to 0. Let's take note that to be able to use the second derivative test, f double prime must exist and f prime at c is equal to 0. Remember as well that the zero derivative means that we have a horizontal tangent line at x equals c. Now if in addition we have that f double prime of c is less than 0, which means that we are concave down at x equals c as illustrated below, concave down, horizontal tangent line. This shows that f has a relative maximum value at x equals c. On the other hand, if f double prime of c is greater than 0, which translates to the function being concave up at x equals c, so we have concave up, horizontal tangent line, and hence f has a relative minimum value at x equals c. It's actually a good thing to take note of these two illustrations as they will help you remember the conclusions of the second derivative test. Lastly, if f double prime of c equals 0, we have no conclusion. This means that f may or may not have a relative extrema at x equals c. For the third condition, let us look at some examples to show that indeed we cannot decide if the point is a relative extremum point. Our first example is f of x equals x cubed. For this, f prime of x is 3x squared, f double prime of x equals 6x. Note that f satisfies the hypothesis of the second derivative test at x equals 0 because f prime of 0 equals 0. Now computing for f double prime of 0, we get f double prime of 0 is equal to 0. But as you can see here in the graph of x cubed, f has no relative extremum at x equals 0. But for our second example, which is x to the fourth, f prime of x equals 4x cubed, f double prime is 12x squared. Again, f satisfies the hypothesis of the second derivative test because the first derivative at 0 is 0. F double prime at 0 is also 0, and as you can see here on the graph, f has a relative minimum at x equals 0. These examples shows us that if f double prime at c equals 0, we may or may not have a relative extrema at x equals c, and hence the second derivative test gives an inconclusive result. Let us continue with some examples where we apply the second derivative test. In the next examples, we want to determine whether or not the second derivative test is applicable to f at each critical number. This means we only need to check that f double prime exists and f prime at that critical number is 0. If yes, we draw conclusions using the theorem. Our first example is f of x equals x to the fourth plus 2x cubed, with critical numbers 0 and negative 3 halves. You can pause the video and try to solve for the first and the second derivative of this function. You can verify that f prime is 4x cubed plus 6x squared, and f double prime is equal to 12x squared plus 12x. Our next step is to substitute the critical number in the first derivative. We see that f prime of 0 is 0, and f prime of negative 3 halves is 0. Since both are 0, this means that the second derivative test is applicable to both critical numbers. Our next step is to substitute these critical numbers to the second derivative. F double prime is negative 3 halves is equal to 9, which is positive, and since the second derivative is positive, by the second derivative test, we conclude that f has a relative minimum at x equals negative 3 halves. So positive second derivative, relative minimum. On the other hand, f double prime of 0 is equal to 0. That means we have an inconclusive result. Great. Next example. F of x equals x squared all over 9 minus x squared, and the critical number is 0. Again, you can pause the video and try to solve for the first and the second derivative of this function. You should be able to verify that the first derivative is 18x all over the quantity 9 minus x squared squared, and the second derivative is given by 54 times the quantity 3 plus x squared all over the quantity 9 minus x squared cubed. The critical number is 0. Let's check for f prime of 0. This is to show that f prime of 0 is 0, which means we can apply the second derivative test. Now f double prime at 0, so if we substitute 0 here, we will get this value. So even though we don't evaluate this, we know that this is positive. So positive second derivative means that we have a relative minimum at x equals 0. That's really nice. Let's go on to our third example. Now f of x equals negative x raised to 4/3 plus 4x raised to 1/3, and the critical numbers are 0 and 1. F prime of x is this one, and f double prime of x is this one. Again, you can pause the video and try to verify that indeed the following are the first and the second derivative of f of x. Now let's substitute the critical numbers. F prime of 0 is 0. F prime of 0 is undefined. F prime of 1 is 0. As you can see here, f prime of 1 is 0, but f prime of 0 is not equal to 0. And hence, the second derivative test is only applicable at x equals 1. Now let's check for the second derivative at x equals 1. Substituting 1 and f double prime, we should get negative 4/3. You can verify this, which is less than 0. So we have negative second derivative. By the second derivative test, f has a relative maximum value at x equals 1. So this ends this part of the lecture. The second derivative test for relative extrema is actually useful in some word problems in optimization that you may look forward in later lectures. Alright, for the next part of the lecture, we will be looking at how to use our knowledge of relative extrema and concavity to graph functions, starting with polynomial functions. See you on the next video.